those gray boxes now.
Yeah.
Are you in like detached?
Hey everyone.
So we're just letting a couple more folks in here and we'll get started shortly.
So if you're a team lead or planning to present, make sure that you taking a look at the top bar, hopefully, or if you're on web browser at the bottom bar, you'll see the option to share. I wouldn't try it out just now, but just click around and make sure that you kind of get to know that interface a little bit. And hopefully, if you have any trouble, we can help you out. We know that this is the first time sharing on WebEx for a lot of you.
All right, so it looks like we've got a majority and we can go ahead and kick off our hackathon ceremony. I'll be running this portion of the event. If you don't know me, I'm Lucia Darrow and co-chair and project manager for the Datajam. So just briefly, I wanted to go over our schedule for this evening. From 6:30 to 7:30, we're going to be doing our demos and voting for our top 3 teams. And then 7:30 to 8:30, we have an awesome career panel with some experts from industry as well as academia. And then at 8:45, we'll join back together and let you know our winners for the evening and do our closing ceremony. So we only have 1 hour for 9 demos. So we're going to go ahead and jump into our project demos. These are going to be 3 to 5 minutes. And I'll ask everyone to please turn off their cameras unless you're presenting for this portion of the event, just so we can keep our bandwidth good for our presentations. And if you have any questions, unfortunately, we're pretty short on time, so I'll ask you to just post those in the general channel on Slack, and then the teams will be happy to answer them there. And our voting process for this evening, we'll be sharing out a Google form where you can select your top 3 teams for the evening, and please take notes throughout the presentations. Consider what you find to be the best projects in terms of, both the projects themselves, the format, the styling, as well as their impact and how they play into our theme today. So with that, I think we'll go ahead and jump into the first demo. We're going to go in order of the project numbers as they were shown on GitHub. So we're going to start off with project 1, which was looking at the citizen science aggregate global plastics litter data and applying some forecasting and machine learning methods. So I'll pass it over to Zaid from Team 1 to start that demo.
Hello, everyone. My name is Zaid, and I'm the team lead. Oh, I'm sharing the wrong screen, my mistake. Screen 2. Hopefully this works for the second time. All right. So my name is Zaid. I'm the team lead for the Citizen Science and Machine Learning team. And today I'll be talking about the Earth Challenge integrated data for the plastic pollution. So for our problem here, we have the data set from the Global Marine Litter Baseline. We have 3 sources of data sets. And our problem, as has been shown in the talks this morning, that plastic pollution is a major problem in our environment and oceans. It keeps coming up to our oceans and other water bodies. So we're hoping to identify the hotspots and the kind of project and forecast the plastic accumulation to plan for better cleanup resources and events. And on my team, we have Lavinia, Nabila, Tushi, Daniel, Young, and Will. The mentors, we have Matt and Priyanka, and myself as the team lead. For basically, as we can see here, that the plastics have been growing more and more in terms of volume and also over time. And the primary land is basically the major problem for acclimating the different plastics and pollutants. In order to do that, we thought first we can start with the hotspots map. That's an interactive map. It can help organizations identify the hotspots over time, and we can select and have the ability to zoom in and identify where the hotspots and major problems to help in deploying or at least planning the resources. We also have interactive regional maps to have the ability to dig deeper into the different shorelines and different hotspot problems. Building up on that, even though this is still a proof of concept, we were able to get a predictive modeling attempt. It's not doing so great so far, but at least that's we were able to get in a short amount of time to predict the number of volunteers needed or resources needed to do the cleanup. And quickly, just going over the interactive map, basically our app, if we were to deploy that, we would have the interactive map and the ability to zoom in, identifying the different hotspots with the different years to plan for the resourcing, and then as well as having the regional map with the ability to zoom and identify the different hotspots, and as well as find items at each location. So that's kind of our quick demo. As next steps, of course, if you have more time and more data, we would like to build an improved predictive model to forecast the number of resources and deploy that as an app with the hotspots map and the predictive modeling to enable organizations to be able to predict the resources and the number of volunteers needed, and hopefully expand this globally as we only focus on the Canadian data sets. Thank you all, and let us know if you have any questions.
Thank you so much, Zaid and Team One. That was awesome. I love to see the GG plots and how you focused on Vancouver. So great stuff. And again, if anyone has any questions, put them in the general channel. So we'll move on to our next team. Project 2 is the first team working with the Great Canadian Shoreline cleanup data, and they're doing some visualizations. So I'll pass it over to Casey and Hudson.
Okay, so our team 2, yeah. Our team member Shoreline is going to share his screen shortly. When you are ready, Shoreline, yeah. Hi guys, so we're team 2, and our data set is a Great Canadian Shoreline cleanup data, and we did basic spatial and temporal analysis of the data set to see if we can find any trend and relation. So when we think about shoreline cleanups, a lot of assumptions we come up in our head are: do we pollute more in the summer months, or are there are the most populated cities the most polluted? For example, is Metro Vancouver the most polluted city in BC? And because a lot of people are nowadays concerned about plastic waste. So I also want to know that is plastic waste growing the fastest? And we're going to dive deeper into those questions. I'm gonna pass to my team member, Carol, and she's gonna talk about spatial analysis.
So we have separated our data into plastic and non-plastic waste and compare these in 2 maps. So the numbers are pretty small, but we can see that in the prairie provinces, the ratio between plastic and non-plastic waste are pretty similar compared to the rest of the country. And also, we have a hypothesis that the West Coast have a lot more plastic waste compared to non-plastic waste. You can see the numbers are almost tripled or doubled for certain areas, but that's just a hypothesis for now. We have to dig more into it to verify that. Okay, gonna pass it to Siobhan.
I think someone is sharing the wrong screen by mistake.
Yeah, Siobhan. Yeah.
Now it's good.
Oh, Siobhan, we can't hear you. Are you on mute?
Yeah, can you hear me now?
Perfect.
Okay, thank you. Sorry about that. Little technical glitch there. So yeah, so now what we want to do next was we want to check the provincial ocean waste trends. And so we did a plot of the total amount of kilograms of waste as opposed to the provinces. And it's clear to see that BC and Ontario are the most polluted provinces. And we also did a plot on the left, and it confirms that we can see that Ontario is and BC are the most polluted ones. So we decided to like dive deep into that and check if our first assumption proves right. So what we did is we wanted to see the top 10 highest polluted cities in 2017, and surprise, no Metro Vancouver on top. It was actually the city of Port Coquitlam. So that was quite interesting to us to see, and so we wanted to check it further. And in 2018, we found that the city of Chilliwack was the most polluted city in terms of ocean plastic waste, which was quite surprising as well. And then in 2019, we found that the BC Provincial Parks was the most polluted municipality. That was quite interesting to see, and it kind of really took our assumptions to the side. Yeah, now I was going to talk more about temporal analysis now.
All right, so in addition to looking at the spatial distribution of the data, we also looked at some of the most common types of waste over time. And we saw that consistently over time, cigarettes and tiny plastic are top in the charts, although tiny plastic hasn't increased as much. We also looked at the top 5 most common sources of waste for different years, and as you can see, those remain relatively similar. So yeah, it's always cigarettes, it's always tiny plastic and food containers, bottles, things like that. We checked to see if there were any interesting seasonal trends, and we noticed that it's more common to pick up cigarettes in the spring. It's more common to pick up tiny plastic in the summer. Why that is, we don't know, but that's an interesting question. We also try to categorize types of waste. So we looked at some of the most common household items that are found during shoreline cleanups, which are plastic bags, and then the most common food and beverage items that can be found, which is usually various types of food wrappers and containers. So we also check to see over the years which types of waste have seen the most growth. So like which types of waste we're seeing more and more of. And cigarettes not only are the most commonly found items, they're also like the type of waste with the highest rate of growth, in addition to paper bags and plastic bottles. So that's perhaps something to look out for in the future. And last but not least, we wanted to look a little bit at the chemical composition of the waste that is found during shoreline cleanups. Given that we didn't have particularly granular data, we just decided to look at plastic versus non-plastic waste. And we saw that predictably both plastic and non-plastic waste that was collected increased over the years, but surprisingly more non-plastic waste was collected over the years, and it grew rapidly, especially between 2017 and 2018, which was unusual for us.
Thank you, Yana. Can everyone hear me?
Yes, we can. Thank you.
Yeah. We did some analysis on the pollution trends by month also. This plot is months against the total amount of waste for each year, but the number range is too wide, spanning from 0 to 400,000. So in the next slide, we we plot the amount of waste in log scale to see it more clearly. From the plot, it seems that the number is increasing gradually each year, and that the summer is has more waste than non-summer period. But are these assumptions true? To verify this, for the first assumption, the number of wastes each year is probably caused by a difference in the number of cleanup events. We plot the months against the number of cleanup events and find that 2019 has more events. Therefore, it has larger total amount of waste. And then for the second assumption, summer has more waste than non-summer period. We introduce an average waste, which is the total waste divided by cleanup events. If summer truly has more waste, we should see summer average waste larger. But from the plot, there are no obvious patterns regarding summer versus non-summer periods for average waste. Therefore, the assumptions cannot be easily drawn. And then next, over back to Casey for recommendations.
So from our analysis, we found that cigar and paper bags have the highest growth rate. So we will recommend cities to install more cigar bins. And as for paper bags, many people think they are environmental friendly, right? But actually from a research paper from Northern Ireland Assembly, it indicates that paper bags actually takes like more than 4 times energy to manufacture. So those bags definitely add to the carbon footprint as well. And also our spatial analysis indicate that the most polluted cities are not necessarily the most dense areas. So we would recommend to increase shoreline cleanup in less densely areas as well. And from our temporal analysis, we did find out that there are slightly more cleanup activities going on in the summer. So our last recommendation would be to encourage people to go out and clean up more during the winter times as well. Yeah, so this sums up our presentation. I hope you guys liked it. Yeah.
Thank you so much, Casey and Team 2. Great presentation. I love how you walked us through your kind of analytics and exploratory process. It's really cool.
Thank you.
So next up, we have Team 3, which was working on image classification. And I know they're probably faced with the challenge of not enough data, as is always the challenge with image classification. So I'm looking forward to hearing how they handled it. Pass it over to Zubia.
Okay. Yeah, Warren's going to share his screen. Okay. You want to do the slideshow, Warren?
Sorry, can you hear me?
So yeah. So Warren will be presenting our project today, but as a team, I just wanted to introduce my team. So the team for Project 3 includes Maddie, Sagar, Selena, Warren, Nasreen, Hans, Kevin, Amir, and myself. And we came up with WasteNet. And Warren will talk more about what we accomplished as a team today. So take it away, Warren.
Thanks, Zubia. So our team at WasteNet tries to use image classification to identify waste categories in order to sort recyclables more easily and reduce contamination in our trash. So our team used Gary Thong's TrashNet data found on GitHub, and our team looked at 2,500 images spread across 6 different categories, which are cardboard items, glass, metal, paper, plastics, and trash. The data was distributed using a 70-15-15 split for training, validation, and test. And one of the caveats of this dataset was that the trash class was significantly smaller, like about a quarter of the rest of the data. But this will be addressed during the training process. So as a starting point, our team used a conventional SVM model. So that was our baseline. And we can see that the the model had a training accuracy of 90%, like 90.7%, which is pretty high, while the testing accuracy was 64.6. We can see on the confusion matrix that we had misclassification across all 6 different classes. So that clearly was not making the mark. And to improve on our model, our team moved on to using ResNet. So our team used a transfer learning on a pre-trained ResNet with a added linear classifier and fine-tuned it afterwards. We also used weights on the different classes in order to compensate for the imbalance of data. So our trash had a 1-to-4 ratio. And this new model was actually able to get a 98% accuracy on the training and a 93% even on the test data. So that was really exciting. We can see on the confusion matrix that we have a lot more true positives and way less misclassification across all, with the exception of trash data, which had more mixed results, but still very good. So our team used 25 epoch, and we can see that even on the first 10 epoch, accuracy increased drastically, and loss was also reduced by a lot. There is a constant improvement of the results, with high accuracy over the rest between the 10th and 25th epoch, with also losses reducing within the remaining 15 epoch. So these are some of our result samples. So the model was able to correctly identify glass pieces as glass, even when there's like a label on, cardboard pieces, and paper pieces. Some examples of cases where it failed would be actually cases that even with the naked eye is actually pretty hard to do. On the top right-hand corner, we can see a circular paper plate that was identified as a plastic item, probably because of maybe the reflection. And the crumpled one right on the left of it was identified as metal. And these are actually hard cases to do. So our team got really excited about our results. So we got out of our seats, opened our door, and went to hunt for our own data outside using our phones. So in order for us to see if the model would actually generalize with things outside our data set. And it actually did. So on the left-hand side, we can see a piece of cardboard that was correctly identified as cardboard and a chocolate wrapper identified as trash. On the other side, on the right-hand side, we can see some cases where the model actually failed. And these are cases where there was less accuracy due to a more complex background, with like the plastic bag and the paper cup, trash cup. And this leads us to the discussion portion. Our sample data were great in a controlled environment where we had a nice background, a solid color background. The data was trained on like a single camera or like a few number of cameras and a single object per image. Other ways the model was slightly biased was that the sample size was relatively small, even though we used a pre-trained data to get better results. The data we took from was had about 500 images per class. With the imbalance of the trash items, which even though was adjusted with weights, inherently the raw data was lesser. So ways the model could be improved would be using integrated object detection in order to label image in real time and kind of get rid of the noise of the background. We could also use more sophisticated data sets with more sophisticated data labeling and more variation in the data in order to train the model. And the model could also be further improved in terms of classification using contrastive learning. So thank you very much. That was WasteNet.
Thank you, Warren. And thanks to the rest of Team 3. Great job. It was cool to see how you guys pulled in your own photos. I'm sure the maintainers of the image repository would be happy to get those as well. That's awesome. So next up, we have Team 4. And before we jump in, I do just want to remind our team leads that we're shooting for 3 to 5 minutes for each demo. But we'll jump into Team 4, which is our first application. And this is the plastics footprint app developed by Ore and his team. So I'll pass it over to you guys.
Hi, everyone. Can you see me? Let's see. One sec. I need to share my screen. Sorry. There we go. Sorry, we don't have any fancy slides, but we're just going to walk you through the application itself and then give you an overview of the way we approach the problem and what we plan to do moving forward. Yes, so I'm Ore, just like I was introduced, and I worked together with an amazing team of 4 other people, that is excluding the mentor themselves, and it was Sun Kim, who was our mentor. We had Caitlin hacking with us, Amanda hacking, Leanne, and Rosalind also hacking with us on the project. And the goal was to essentially enable like individuals just like you and I to actually go ahead and actually track their plastic waste footprint. And in this case is just being able to compare and see how you're doing in accordance to like the average Vancouverite or the average Canadian. And for this work, we had some data sets from the actual Vancouver. There was a trying to find the right word for it, but there was a Metro Vancouver study actually that did go out and collect data on waste sort results from different types of families. And so they did it on single families, multi-families, industrial areas, and actually going into like drop-off zones. But for our case, we decided to actually pick from that data set itself the sample that went deeper into plastics. And we wanted to scope things down into what was actually quite achievable within the short time we had. And so what we went with, without like talking for too much more time, was that we decided to go through 2 points. Our application was supposed to solve essentially 2 things. One, enable like an individual to actually plastic waste. And so that is defining the type of plastic waste that you have and the number of like plastic items. To save ourselves during the implementation time, we actually kind of hard coded the weights based on the data set that we kind of had in there. But obviously long term is making that dynamic, you know, maybe based on the rolling averages or letting the user actually impute the weight if they have for some way like a scale in their house to measure their plastic. And what we went on the other side was to be able to actually, first of all, visualize. In this case, we have some user data in here that kind of shows how the person entering the data is doing compared to single families and multi-families, and then also breaking it down based on the plastic type, in this case, the type of plastic that you're using. And on the other hand, what we wanted to do over here was kind of show your plastic breakdown over time. And this is more like just kind of giving you an idea of what you are actually essentially consuming more of, or what you need to kind of, I guess, watch and see how things drop. Obviously, there was a lot of plastic consumption today, and that's why this is quite high. But yes, I'll just go ahead and just like try and do a quick little demo and pick like 10 counts, I guess, film. Plastic itself, maybe 100, just to kind of make things jump up a bit. And so when you track this, it does record the data itself. As part of the limitations right now, we actually have to kind of restart the server. Just because the client that we use, which is Dash, doesn't actually update the data ahead. It kind of, I mean, this is something we need to work ahead and change in the future. But I'm just going to refresh this right now real quick. Yeah, and we see the film that we just entered over here. And so the idea is that as you go through this on a daily basis or over a periodic basis, you can kind of see how things are averaging. And then you can also compare. And for this comparison view, what we went with for starters was just kind of snapshotting for a particular month. From the data that we had, we only had data for a given month, so we didn't want to kind of generalize over a wide range. We just wanted to go with something to kind of demonstrate the idea itself. And so just over here where I added some more film, you can see the actual amount increasing, and you can actually see how you're doing compared to single families or multi-families based on where you kind of belong. Obviously, as a future thing we can do is increase the number of types or households, in this case maybe industrial areas if bigger companies want to actually track their waste, and possibly make this like easier to impute. So right now, if you look at this, you have to actually understand which category your thing belongs to. And this is why we went with very high level categories. There were quite deeper categories in the data set, but obviously it's kind of hard for individual people to know which specific group that it belongs to. And I guess we can obviously work with the other app, the WasteNet now, and possibly even use the input from that into this, possibly if it kind of breaks down into smaller sizes. But yes, this is just a quick overview of the work that the team did together, and it was just being able to, one, allow you to enter the type of plastic waste and track that, and you can actually see your breakdown as increases over time based on it itself, and you can also compare together with other families in this case around you. And I mean, there are different levels you can take this to. If you want to play around, you can maybe have people's families compare with other families, and it becomes a game. Your plastic usage as low as possible. But yes, that's all about it from me. And yeah, thank you, everyone.
Excellent.
Stop my video now. Hope I didn't take too long.
Thank you so much, Ray. I love the use of Plotly and the comparison to the average Vancouverite. It's a really cool tool. So next up, I'm going to introduce Jeanette, who's going to talk about Twitter sentiment. So we'll be dealing with some text data.
Okay, so I'm going to start the presentation. Okay. So we are Team Twitter Trends, and our hackers for today were Jerry, Willie, Simon, Juanita, Rita, and our mentor was Madden, and myself, I was the team lead. So the question we wanted to answer today was, what are people's sentiments towards different sustainability initiatives, whether that is positive, negative, or neutral? We did this by collecting Twitter data. We used Tweetbee, which is Twitter's API, to find the tweets that contained hashtags with sustainability-related issues. And a lot of our project was involved a lot of cleaning and collecting data. And so the process of cleaning took probably more than half of the entire hackathon. We did things like remove stop words or remove emojis, and filtering to only collect the text that was in English. We also tried to extract the locations, and then we tried to use the locations to attach kind of the coordinates in order to make a plot on a map, but unfortunately we didn't have enough time to finish this. So as you can see, here is a little sample of what our data looked like, and it wasn't consistent or clean or pretty. And another limitation of our data is that the Twitter API only lets you collect data that is a week old, and so our analysis is based on only week-old data. So our sentiment analysis, we used a range of -1 to 1. -1 is negative, is more of a negative sentiment towards in the tweet, and 0 is neutral and 1 is positive. And then we also collected n-grams of which are sequences that most commonly occur in these tweets. And so these included words such as activism, plastic, sustainable living, no plastic, or ecology. And so here we have kind of a comparison of the sentiments among the different hashtags. So no plastic has a negative, 18% of the tweets had more of a negative sentiment, and 51% of them had a more positive, and this is the same for pretty much all of the hashtags. Most of them were pretty positive reactions or sentiments towards the tweets. And then here we also have a graph of the most common trigrams that occurred. So yeah. So we also created a word cloud of one of the hashtags that we did collect, which was sustainability. And then I'm going to pass it on to our mentor, Madden.
Yeah. Hi everyone. Thanks, Janet, for passing on. So I'd like to continue with the with the presentation. Until now, we have seen like perform some sentiment analysis and see and observe like how people have reacted to plastic crisis and sustainability and so on. So as an extra aspect in this project, so we wanted to sort of build our own generator using the data set that we have. And so what we did is we built a neural network with like a recurrent neural network, and we used gated recurrence units for that. And so how it works is, so if you give the starting word, let's say like pollution, or let's say like sustainability, so based on the first word, the entire tweet is going to be generated. And as Janet mentioned, the one main aspect about Twitter API is that it doesn't provide lots of data. So with the new restrictions, it just allows you 7 days of access. And we know how hungry neural networks can get, and how lots of data is required to train the neural networks. And so I think that is going to be one of the major setback which we had. And what we did is we packaged this entire neural network, and we sort of have built some APIs, and we quickly deployed it in the AWS service, so that we can sort of see how it works. And if you at the bottom, if you see that it says plastic Europeans, so that is one of the tweets that has been generated. Actually, we can take a look at one example in the application itself. So this is a simple application that we have. So the starting word can be anything. So if you give waste, so it's going to generate a tweet of 280 characters. So so waste could be one word. You could use lots of other words as well. You can sort of try pollution. So it is going to generate different results at each like when you invoke it every time, it's going to give you different results. So the data set that we have is really small. So we have 5,000 to 7,000 tweets. So provided that we had more tweets, our results would have been even more fine-tuned. So now back to Janet for the limitations and improvements.
Yeah, so as we mentioned before, the Twitter API has a limitation of only 1 week. So it would have been nice to collect older data, but that kind of was beyond our skills and expertise. The model also could not take into account for non-English users' sentiments. We only filtered out English tweets because the package that we used, the sentiment analysis only worked in English. Also, we did want to use geo-coordinates to plot and compare the different sentiments across US and Canada, but we had limited time, and the data cleaning for this process did take a lot of time. And another limitation was the difficulty in differentiating between tweets that were ads and products versus actual real people. So these are issues that we would have solved if we had more time during our hackathon. So yeah, thank you.
Great. Thanks, team. That was awesome. I love how you went above and beyond creating that bot. We've got some stiff competition today for sure. For our next group, I believe we have a video recording, and this team was looking at the salmon life cycle in the Comox Valley. So I believe Lisa is going to share out this video.
Yeah, let me just do that.
Hi, we'll be presenting a team modeling salmon life cycle. This is done as part of the Vancouver Datajam. First off, we'll start with a land acknowledgement. So we acknowledge that the work that we did was on the traditional, ancestral, and unceded territories of the Coast Salish peoples, Squamish, Tsleil-Waututh, and Musqueam nations. We are very grateful for our time, and we're very excited to share with you this work. So our team had two main sub-teams, web scrapers, Rachel Dunn, Anouk de Bruber, and Jensen Lin, and the modelers, myself, Courtney Van den Elsen, and Pierre Vadani. So I'll start by motivating our problem. So this is work that builds on top of a project called Callisto, and I'll stop sharing presentation for a second to show you. So this project is done through the CanCode program and is done in partnership with the Pacific Institute for the Mathematical Sciences as well as Cyberra. And so in this first problem, what we do is we model First Nations traps. These are intertidal modifications that are used and depend on tide behavior to catch and harvest fish. So the initial model focuses on the Comox Valley Harbor area, and it uses or depends on the tide behavior for that area. So in the first iteration, we study the tide for day one, week one, and then we can go ahead and do things like model the behavior of the trap. So in this case, we get to choose how much we want to harvest. We assume a finite number of fish. In this case, we assume 1,000 fish. And then we can change the parameters of our trap to change how many fish we get. So in this iteration, we want to extend this work to include a number of additional assumptions. Instead of constant fish, we want to incorporate the long-term population size for salmon. In particular, we'll be focusing on Chinook salmon. The other thing we want to incorporate is tide behavior for at least 3 years. And we want to incorporate the role of microplastics in the population. So those are our two goals. One, role of microplastics in the changes in population, and then two, the differences between two fishing models, industrial fishing and intertidal modifications, which rely on tide behavior. So from here, I'll pass it on to Anouk, who is one team member from the web scraper team, to tell us about the work that they tackled.
Hey, thank you, Laura. So we were tasked with scraping the Government Canada website. As you can see here on the left, it has a column for each month with the day, the time, and the tide level that was recorded. And our task was to get this data and eventually turn it into a pandas data frame or a CSV file with a timestamp and the height of the tide. Okay, so we used Beautiful Soup and requests. So on the right, you can see when we parse the HTML with Beautiful Soup, how beautiful the soup is. Very messy, but you can use the classes and this to access the different types of data. So that's what we did. We looped over each what was originally a table and now turned into 1 month of soup to get the date and the time and the tide heights, as you can see in the snapshot on the right here. And then eventually we managed to create a pandas data frame from the lists that we got from the soup and turned them with the heights. And finally, we made a visualization in Matplotlib. Yeah, so overall, we spent a lot of time figuring out how to get things working, of course. Particularly, we spent a lot of time converting date strings that we scraped from the HTML into a date time format in Python, and then realized that actually Python pandas is totally fine dealing with date strings. So we didn't have to do that. And yeah, time flies when you're coding. You're muted, Laura.
Thank you. So I'll jump into the modeler work. So we are focusing on modeling salmon population dynamics along with fishing and microplastics. So the questions of interest include how is wildlife, and in particular the Chinook salmon population, impacted by plastics and industrial fishing? Another question is, assuming we harvested like First Nations people did, that is, if we incorporate tide movements and we work along with tide movements, how would that be impacted? And then third is, how can we change our current fishing practices towards sustainability? So what we did is we built a discrete time mathematical model that allows us to assess the impact of commercial fishing and ocean plastics. And then our hope is to then build on top of this model to compare the impacts of indigenous fishing method versus the commercial one. So we based our work on an existing model, and we included a number of additional assumptions. We get same death rates by different causes, natural causes, fishing and plastics, and assume that the death rates are the same. We want to incorporate a new assumption that plastics affect death rates of adults and impact reproduction success rate. We don't really know what that number is, so our aim is to attempt different values in our model to see the effect of different rates of impact towards reproduction success of the salmon. We assume that death rate by plastic is the same, and that fishing or harvesting practices are applied when salmon are adults moving from the ocean back to the river. So we are curious to know what the impact of ocean plastic is via direct ingestion of microplastic, secondary ingestion by juvenile salmon, and because we don't really have a lot of data on this, or really we couldn't really find data on this, we're kind of basing the study on guess. So we create a flow diagram for the life cycle of salmon as it moves through the different stages. And then this DN over here indicates natural death. This DP, once the salmon goes to fry, then it can start ingesting plastics. So not only can it die from natural causes, but also from plastics. And then once the salmon is in adult stage, then they can die from ingesting plastics, natural deaths, or by fishing. In this case, we assume only industrial practices. So next we incorporate tide behavior. So the model is exactly the same, with the exception that we have an additional fishing cause. So this DF1 incorporates industrial practice, DF21 and DF22 incorporate First Nations practices with intertidal modifications. So the model is, we are assuming that the number of eggs per year is equal to the spawners 3 years behind, times an exponential rate. So this is a discrete model that is still under work. We still have to incorporate the plastic effect, the environmental conditions, which is adding a random a variable to incorporate how this impacts populations, the fishing deaths, and the plastic deaths. So we've added our work in the Vancouver Datajam, and we're very successful in our work and in working along one another. So our next task is to design and implement a system of equation that allows us to follow our assumptions, test the impact of plastic, incorporate the tide behavior, and finally test the differences between industrial and tide-based harvesting practices.
Stop sharing, and now you could see what my YouTube recommendations were.
Thank you to Laura and Team 6. That was absolutely fascinating, and I look forward to reading your journal publication, which could probably come out of that presentation.
Thank you.
Up next, yes, thank you. Up next, we have Team 7 that was working with that, back again with that large citizen science data set to create a visualization. So I'll pass it over to Oshin. Oh, you're on mute.
Alrighty. Hey, can you hear me? Awesome. Okay, so I have shared a RStudio Connect link in the chat. That was our intention as a nice to have at the end to publish to RStudio Connect. As with all great group hackathons, the wheels fell off a small bit at the end with the integration. But we had I think we had some great work before that. So just the final publication, aspect ratios are off a small bit, but it's just a nice introduction. I'm a big fan of RStudio Connect. So in terms of the project, we talked about what topics interest us the most, and over time brainstorming we found time series and location geo mapping. So we split into two teams, and I'm going to pass it over to some of my colleagues, Heather, Rishab and Kaylee, going anti-clockwise through these plots, and they can tell you a bit more about the challenges they faced and the sort of answers they were trying to get from the plots they were creating. So yeah, I'll pass it over to Heather first, who did the leaflet plotting.
Yeah, cool. So thank you. So we started by thinking about how to divide up all of this data that we got to make it more understandable. And we thought about two specific aspects with regard to this spatial distribution, which I worked on the top here. So one was where the plastic was, like which coastlines. So Kaylee wrote some really great code which split up the data into, for example, west coast of North America, east coast of North America. We kept Southeast Asia as one because there are so many different coastlines. And then Tiffany went through and divided up the different types of plastic that were described into hard plastic, soft plastic, plastic from marine sources, and then other, which didn't fit into any category. And then we did these pie charts showing the distribution of those 4 types of plastic in each of the geographic regions that we looked at to see how that varied around the world. And then the other team, the time series team, also looked at some time series, so I will pass it over to them.
If you could zoom in on the next plots, that would be great.
I would love to, but honestly, I don't know how. And that was one of our, one of the things that we would have loved to do if we have more time is to stretch out these other 2 plots so that they fit the windows and they're zoomable. Unfortunately, we totally ran out. The top one is zoomable, so that's really cool, but the bottoms are just like that. So I'm really sorry, but
to viewers, if you're watching on the WebEx app, just right click on the window and then hit view, and then you can zoom in like up to 400%. So if you're having a hard time seeing, just do that.
Thanks, Lisa.
So hi, thanks for the introduction, Heather. And so I worked on the time series data that we had, and we really tried to see whether each type of plastic, so hard, marine plastic, soft plastics, and other, was changing over time globally. And one thing that we found that was really cool is that if you see the spikes, it seems bad, but those are actually during World Coastal Cleanup Day, which is in September. And so this actually indicates that every year the number of people who are coming in and actually cleaning up the coastline is increasing every year. But I don't know if you can see this, but this is a bit sad. The majority of the plastics they find are actually soft plastics, which tends to be harder to recycle and easier to sort of get eaten by animals and those kind of things rather than the hard plastics. So yeah, that's a negative that we found. And then Kaylee worked on the last graph where we looked at a specific instance in time. A specific region.
Yes. We originally, as both of my colleagues mentioned, this is a global data set. So our first kind of journey was, how do we break this down into something like meaningful chunks of information? And so one thing we were thinking about is how there's been a lot of plastic bans in recent years. And you can see our data set starts in late 2015 and goes till just early 2019. We had originally hoped to produce many of these graphs, like the bottom right one, focusing in on specific legislation in many different regions, and sort of looking at plastic waste on shorelines as some sort of proxy for plastic consumption around before and after these legislative events, points in times that say use less plastic. We didn't get around to that, but what we did get around to is for Southeast Asia, you'll see the data added here. These are all shoreline cleanups in Southeast Asia between 2015 and 2019, early 2019, that is. And this big red line is when China stopped receiving plastic, or they put a big ban on a bunch of the plastic that they received. And prior to this line, China received 80% of the world's recycled plastic. And so we were really interested in looking at, after China stopped receiving this plastic, do we see an increase in the amount of plastic showing up in Southeast Asia, which is shown to be receiving a lot of the plastic that was previously routed to China? And so we don't have a super clear answer here. It's not, we didn't get far enough to sort of really indicate what exactly is going on. Perhaps we could look at total plastic. But that was sort of the sentiment that drove this. And if we had more time, I think if we had a larger data set, we could kind of look a little further in time, since 2018 is a fairly early benchmark for when a lot of these legislative events were happening. And yeah, we could really zoom in on more of these sort of smaller regions and countries to see how specific legislative events affects local plastic pollution. So yeah, that's it.
Awesome. Thank you so much, Team 7. These are some beautiful visuals, and this is actually a perfect tie-in, I think, to our next presentation. So our next talk is going to be from Team 8, which was, again, looking at the Great Canadian Shoreline Cleanup data, and actually looking at this relationship between legislation and shoreline waste. So I'll hand it over to Keegan.
Hi, everyone. I'm Keegan. Oh, is there? I'm not seeing a share button.
We might need to make you presenter. Let me see.
Oh, you know what? I need to change my system preferences. So sorry about that.
Give it a shot now. I just made you presenter.
Yep. So I have the button, but it's grayed out, and I have to change my system preferences. I think I might have to jump out of the meeting and jump back in for that to take effect. I'm so sorry. It's my computer blocking me.
Yeah, that's fine. Feel free to do that. Hey, Keegan, do you want to try again?
Yes. Now the button looks much better. All right. So everyone should see my screen now. Great. So we're Team 8. So we had 4 awesome hackers, Sandy, Roshni, Almas, and Catherine. And we also had a super R mentor of Ariane, who was great on getting us when we were stuck on different tasks. So yes, our project was dealing with the Great Canadian Shore Cleanup data and linking that with plastics ban data, so municipal ban data. So just as a reminder, the shore cleanup data is detailed, rich data of what types of plastics are found at each cleanup over the past 3 years of cleanups, 2017, 2018, and 2019. And the retail plastic bans data, we used this website, from the Retail Council of Canada. And this is a great resource for logging different types of plastic bans, as well as plastic straws, utensils, plastic bags, and so forth. It's not so great in that it's not really in a format that we can just analyze readily. So it's in this kind of web format. We can get it to a PDF, but getting it into a nice clean table actually took our data scraping sub-team quite a lot of effort into doing. And so they were able to grab this, if you get the PDF, it's a 60-page long document, and they were able to condense that into a nice clean CSV data set, which we uploaded to our GitHub, which is super useful. And so the main questions we were asking, so I'm going to walk you through a few of the plots that we think are most informative in our summary here. So our main product here is this HTML summary. So one of our main questions we wanted to answer was looking at the types of plastics found and the amounts of plastics found across different provinces and over time. And one of the things we were mainly concerned about is in looking at the amounts of plastics found, we thought that that would be really related to just how many cleanups are happening, how many people are showing up to the cleanups, and how much shoreline they're cleaning. And so if we saw trends across the years, we might be wondering if it's just that there are more cleanings happening, more people showing up for the cleanings, or fewer people. So we wanted to adjust for that. And so that was one of the things we focused on, where our group was kind of focused on the stats. So we came up with this adjusted sort of metric where we take the amount of plastics, so the counts of different plastics found, and then we adjust it for the number of people at the cleanup, as well as the amount of shoreline, the kilometers of shoreline that we're cleaning. So then we get sort of this rate of counts, and then we looked at that across different provinces over different years. We can see mostly it's pretty flat for the rate of plastics found per person per amount cleaned. There are some outliers of those tend to be places where there are fewer cleanups. So it might be that the data is just a little bit more noisy. So can't really read into some of those. For example, this is the Nunavut line, and there are fewer cleanups in Nunavut. So it's hard to say whether that's really a meaningful trend. And then we can also look at, we broke it down by type of plastic for each individual province to see if there were certain trends in different types of plastics. And we can also see which types of plastics are found in higher counts. So we can look within each province, can see some maybe decreasing trends for BC. And again, these are adjusted by person and kilometer. And we see that there's some increasing trends for some provinces. And this HTML again is up on the GitHub. So if you want to look at each of these, you can, but I'll just scroll down to a summary plot where we look at this rate again, but instead of looking at counts of plastics, we're looking at a total amount, which is based on the mass, so the kilograms of waste that was picked up. And again, summarized over each province across years. And again, we can see it's pretty flat, except for there's Manitoba kind of popping out again as having this increasing trend. So they're per person per kilometer cleaned, they're finding more litter. So either these cleaners are getting more efficient, or there's actually kind of more trash on the shorelines that they're cleaning. And then going back to the ban data, municipal ban data. So again, our team got that nicely scraped. And this is kind of a summary of the trends we see there. So a couple of notable things are that BC is actually the only province in the database that has multiple types of plastic bans. The other provinces, although Quebec has the largest number of municipal bans, they're all plastic bag bans, whereas BC has plastic straw bans, as well as food packaging bans. Another trend is over time. So clearly the bans are really a more recent phenomenon, although they go back all the way to 2007. Most bans were issued and went into effect in 2018 or 2019. And in addition, the alternate types, other than plastic bags, the straws and food packaging, are only from very recently, from 2019. And then if we look at that by province, we can see that BC in the kind of mustard color is one of the provinces that's more recently adapted some of the bans, whereas in pink, Quebec, as well as Manitoba in green, they were kind of early adopters way back in 2007 to 2010, issuing the bans. And then, so one of our final goals was to be able to link these two data sets. So this nicely curated ban data that we scraped from the web and the Great Canadian Shore cleanup data with these adjusted rates for person and kilometer cleaned. And unfortunately, we ran out of time to do that too extensively, but I'll just show you my screen of kind of where we left off on doing that. So essentially, we wanted to see before versus after the ban. So this last line here shows in BC, after the ban, we have an adjusted rate of picking up food wrappers of 21.9. And that BC is the only place that has the food wrapper ban, but we can go back to when BC did not have the ban. They had an average of 29.5 adjusted food wrappers picked up. So it does look like there's a decrease after the ban went down to 21 from 29, but we need to do more to understand the uncertainty around that. And as well, it'll be interesting to look at this data going forward when we have more time since the bans have been in effect and understand if there really is a long-standing trend. So that's it for us. Thank you.
Awesome. Thanks, Keegan. I'd really like to see the continuation of looking into that data. And I like how you guys looked at it by person, by kilometer. It's a great way of breaking it down.
Thanks.
So we'll move on to our last team before we jump into our panel session. And this is Team 9, which created a Microfiber Habits application, I believe. And I'll pass it over to Pauline.
Hi, everyone. Yes, last but not least, and I'm going to try to keep it short and sweet. Loved all the presentation, and I'm excited to what is coming up next. So let's jump right into it. Thank you, Lucia. Yes, we're the team that worked on the Microfiber app. So here we go. I'm going to share my presentation now. And our challenge as a team, hold on. Ooh, sorry about that. Yeah, so we started with this challenge that was given to us is based on research. It indicates that home laundry of your textiles, your clothing, is a big contributor to microplastics in the ocean, which are then ingested by marine plankton and move across a food web, so a massive source of pollution. It's something that is not really known by the general public. Like I myself, I try to be more self-conscious. I thrift everything secondhand. So if you need any tips on that for Vancouver, I know all the good places. But I was not necessarily aware of that, right? So there is really a need to educate the public on what clothing they buy and how they wash them and how that is like generating pollution. Being aware of that is a first step potentially in reducing it, right? So that was what we've been cramming on today. And our solution was know your impact. So using, making people understand that using simple procedures, you can easily, I would say, reduce the amount of the microfibers you produce. So easy thing, I would say, such as, using your washing machine on cold, using softener, using a front load washer, and using a lint trap, like a trap that captures the microfiber from your clothing. Those are all things that you can incorporate as a consumer and contribute to reducing the pollution of microplastic. So I'm going to take you now to our app. So that's our MVP. We chose to focus on one data set. There are many different type of data we could have generate and showed. one of the main challenge of our team today, what we spend a lot of time on, is actually finding the right data set and making them fit for purpose and making calculations for the application. So, you know, we took one aspect, one type of data, as you can see right here. We have the microfiber loss per different type of textiles. So whether you use natural nylon or polyester clothing, that generated more or less pollution. Also, as you can see here on the right, whether you use this lint trap, this filter in your machine, has a significant impact into how much microfiber you are releasing. So that's basically the first set of data we've chose to focus on, and as well as you know, giving some tips, general tips to our users into what to do and motivating them into showing them how much it can change, right? Like a lint trap can reduce microfiber up to 87%. So that's not nothing at all. Yeah, so that's the app. I'm going to just go back to our presentation to talk about like the next step, right? What you want to do with those type of products for the general public is growing the product and making it a good fit for user adoption. So making it easier to use and giving more data to users. So here are a few things that we thought of, a few features using image recognition to allow scanning your clothing tag and knowing like what material type your clothes are on. That's easy to do. If you don't want to read your tag, your phone can do it for you. Showing an environmental score to our users, similar to what we do for LEED buildings. You know, we give you a grade. So that could be also engaging, like seeing the progress as a consumer on how you keep doing better as you're changing your habits. Adding the ability as well to input multiple items into the application. So making the application more, you know, dynamic, and where user can actually input their data and see data output that are more specific to their consumption habits. And finally, also like using data to show how smart choices can positively benefit the reduction of microplastic counts in oceans. Sorry, I heard someone saying something. All good. I'm almost done though. Yeah, so just to wrap up here, the process again was relying a lot on like finding the right data sets. What I was really impressed by as a team lead is that our team basically like learned a new framework, built a UI for almost the first time, taught themselves Python in 24 hours, or improvised themselves as designers. And those are really amazing to see in a one-day hackathon. So I just want to finish it up by acknowledging the amazing team I got to work with, and thank you for the mentors as well. You can be really proud of the product you put out today. Thank you very much.
Thank you so much, Pauline. I just want to add that every other team started with a data set from the get-go, and this team had a really abstract challenge ahead of them. So I love that you guys focused on design, and I'd love to see this project grow as well.
Thank you.
Great. So Lisa, if you could share out your screen again. We will give you guys the link to go ahead and vote for your top 3 teams. When you open up that link, you're also going to see some questions related to feedback in the event. We really appreciate any and all feedback that you have. This is our first time doing the Data Jam, and so it's going to be really valuable to us as organizers. And we'll just take a quick 3-minute pause here so everyone can open up and start voting, and then we'll jump into the panel discussion at 7:55.